Welcome to Uncertainty Principle 3, Single Slit Experiment. This is, I am Robert Nemeroff. This is Physics X, Extraordinary Concepts in Physics, where I try to review some of the coolest concepts in physics. So today we're going to review the single slit experiment because we're building up for the double slit experiment. There'll be several lectures on the double slit experiment. So I want to build up with that by doing the single slit experiment as more thoroughly than has been mentioned before, but it has been mentioned before. So no textbook is required. This is an actual class being taught for credit at Michigan Tech. First, I want to take an aside, though, and do a slide that I wasn't able to really do last time involving quantum mechanics. And a thought that has occurred to me, I have strange thoughts. Some of them are actually cooler than others. But what chance is there that h, the quantum mechanic constant, Planck's constant, what chance is there that h is equal to 0? So everything in experimental physics is given some error bars, and with the big numbers involved in many worlds interpretations, how many universes there are and things like that, I thought it might be cool if someone would actually estimate, given experimental uncertainty, the chance that h is actually 0, given every experiment. If true, then delta x delta p could be greater than 0, and maybe the universe would be classical. So there's zillions every second, lots of things happen that indicate there are energy levels that are tied to h. But I'm very curious how large that number would be that we're sure that h is greater than 0. So with that, I'll jump to the next one and say let's do the single slit experiment a little bit more carefully. So here we have a series of photons goes through a single slit, so I'll just draw this here. Photons go like this, and then they end up on a wall. This is the slit screen, and this is the image screen. And I will keep these when I do the double slit experiment starting next time. So what happens depends on several variables. On the wavelength of light here, lambda, which will also be important in the double slit experiment. The width of the slit here, d. It's not all that important, the distance to the screen, although if the screen's right up against the slit, then that's going to negate a lot of the interesting things. So the best single variable might be lambda over d to tell you what's going on. So if we'll go over, also the presence of observers might become important. So let's clear that. So let's say lambda over d is small. The case of, let's say, gamma rays. You try to shoot gamma rays through here. Now, we're not going to allow the gamma rays to go right through the screen, even though they would go through most screens. So we will consider whenever you have an opaque board, this part here is truly opaque no matter the wavelength of the photon. We're not going to allow right now tunneling or driving through or just breaking right through. So when lambda over d is small, you might consider that the photons are like gamma rays and they're like bowling balls. They just go straight through. It's the closest thing to classical mechanics. So diffraction at that point is unimportant. And there will be, if you have a flashlight here and you have a screen here, you'll just get a spot on the screen, just like you would if you pointed a flashlight at the wall. Okay. The next extreme case is when lambda over d is large, greater and greater than 1. So the wavelength of the photons is really great compared to the very small d that's going there. At that point, you're not going to get many photons going through the slit in this extreme approximation. So the classical result is just darkness. So your screen here has nothing. So that's the other extreme. And diffraction is unimportant here because it's just not going through. Okay, the interesting cases are when lambda is on the order of d. Usually d is a few times lambda. So that's the most interesting cases. At that point, you get things getting a little messy and complex, and that the real strangeness of quantum mechanics begins to come out, and the fundamental physics begins to show itself. So what you see is essentially diffraction, which is fundamentally a wave phenomena. So as you go through here, here's the screen, so I'll have to do it up and down here. So here's your source where photons are coming out, and here's your slit screen here. And then here's your image screen. And on your image screen, you're going to get a brightness that looks like this. So I guess you consider this to be your image screen. And here's the brightness distribution where it's going to be brightest in the middle, usually. So you will also get some unusual nodes here. I'll mention them. So here we have classical waves, which this imitates. So here you see there's about 4 wavelengths in this slit size, and here you get the center part, which would just be the center slit in the classical approximation. But here you see there's nodes where you don't see anything here, and you do get waves. Essentially, there are waves that go out even at high angles. So the imaging screen will show nodes where no photons will fall, which is not a classical device, where the screen can be totally dark at these locations. It'll also show that sometimes photons can go way off to the side, and that's also very hard to understand from a classical perspective. So now I'd like to break off and this is well known in astronomy called the Airy disk. You can name things, and different approximations would occur in the near field, the Fresnel diffraction, and the far field, Fraunhofer diffraction. I'd now like to show a little bit of a movie which is made by MIT physicist Walter Lewin, who is an acquaintance of mine. This should take 2 minutes. I might skip a bit so you can play this.
Heisenbergs principle indeed is very, very non-intuitive. Frankly speaking, I'd call it bizarre. But you can see it at work.
Forgive me, Walter, I will skip ahead a bit. Let's hope it plays.
I'm going to make this vertical slit narrower and narrower and narrower.
Photons through a slit,
now you're going to
slit
see?
screen.
Well, you're going to see exactly what you predict. You're going to cut off the edges of the circle.
So he's narrowing the slit.
Gets narrower.
So
and narrower,
D is becoming smaller.
And narrower. But now you come to the point that this narrow slit, say, is only 1/100th of an inch wide. And now Heisenberg's principle comes in. Because now you know so precisely in the horizontal direction where the light is, that as it emerges from this slit, the direction of the light is no longer determined according to Heisenberg's principle. And so now what you're going to see, it's going to spread out in the horizontal plane, and therefore what you're going to see on this projection screen is going to get wider. Extremely non-intuitive. Because what am I doing? I'm making the slit narrower and narrower and narrower and narrower. And what do you see ultimately? That the beam horizontally becomes wider and wider and wider and wider and wider and wider and wider. Now that is very non-intuitive, but it's the way the world works.
Okay, thanks, Walter. So now I'm going to go to an experiment which actually I learned about recently that is essentially 2 single slit experiments and then 1 called Popper's experiment. So I haven't thought this through as well as I have some other things, which doesn't mean I won't get the other things always right and this wrong. But here we have a source that creates pairs of photons. They could be considered entangled, and we'll talk about that later in the course. I have to get this. So it creates pairs that go off in opposite directions. They each go through a slit, and so these slits are going to spread out the photons in both directions, and you will get the same. However, Popper, who was a philosopher, wondered what would happen if you removed slit B. So you take this away. Then what happens? Since photons move opposite of their counterparts, because they're created in pairs here, so momentum is conserved, then the photons passing through slit A are confined still. So if you go back, this slit is still there. That's confining the photons. Do the photons that hit the remaining image screens behind B spread out as if screen B was still there? Popper wondered. So here you see that they're going through here, and the photons would spread out because of the slit here. The photons would spread out because of the slit there. But now you get rid of this one. But still, these photons are being confined. And since these are going the opposite of those, would these be so confined? It's an interesting thought experiment. Popper thought that he was testing the Copenhagen interpretation. But subsequent analysis indicated that he really wasn't, that all the physical interpretations, many worlds, ensemble, Copenhagen, even other ones, would pretty much say the same thing. The answer, though, is no. Although correlations can be found to exist between far-removed particles, even seemingly faster than light, as we'll see with the Einstein-Podolsky-Rosen experiments and things like that, nothing can allow communication like signaling can happen between far removed particles faster than light. So for instance, if you were to keep taking, once screen B is gone, if you keep removing and adding screen A to signal what happens over here, because now you get the particles spread out, they don't spread out, they spread out, they don't spread out, you could be signaling with that. And that would be a form of communication that is just not allowed, because that could happen faster than light. So essentially, these things would go through, and just like as if there was no slit A or B, if it hits here, it would hit the opposite there. One hit would hit here, one would hit down there. So even though they go through this, these guys would still remain collimated. If slit A does not affect what happens over on this side, these photons. The way these things usually work is with correlations. You can sometimes find correlations, not in this experiment. But the Einstein, Podolsky, Rosen experiments dealt with correlations, and we'll be dealing a lot with two-slit experiments where you see a lot of correlations as well sometimes. It seems like particles are communicating faster than light, and certainly they seem one set of particles is doing the opposite of the other set of particles, but you can never signal anybody. You can't say, do this faster than light. That's a limit imposed by special relativity, and Popper's experiment does not get around that. And with that, I will conclude, and next time we will now get to two slits. We've built up to the two-slit experiments, and I'll be doing a bunch of those, and you'll see how really strange that is. See you next time. I am Robert Nemroff. This is Physics X, Extraordinary Concepts in Physics, where I try to review some of the coolest concepts in physics. So today we're going to review the single slit experiment because we're building up for the double slit experiment. There'll be several lectures on the double slit experiment. So I want to build up with that by doing the single slit experiment more thoroughly than has been mentioned before, but it has been mentioned before. But I'm very curious how large that number would be that we're sure that h is greater than 0. So with that, I'll jump to the next one and say, let's do the single slit experiment a little bit more carefully. So here we have a series of photons goes through a single slit. So I'll just draw this here. Photons go like this, and then they end up on a wall. No textbook is required. This is an actual class being taught for credit at Michigan Tech. First, I want to take an aside, though, and do a slide that I wasn't able to really do last time involving quantum mechanics. And a thought that has occurred to me, I have strange thoughts. Some of them are actually cooler than others. But what chance is there that h, the quantum mechanic constant, Planck's constant, what chance is there that h is equal to 0? So everything in experimental Welcome to Uncertainty Principle 3, single slit experiment. This is physics is given some error bars, and with the big numbers involved in many worlds interpretations, how many universes there are and things like that, I thought it might be cool if someone would actually estimate, given experimental uncertainty, the chance that h is actually 0, given every experiment. If true, then delta x delta p could be greater than 0, and maybe the universe would be classical. So there's zillions every second, lots of things happen that indicate there are energy levels that are tied to h.